Good morning, everyone, and welcome to the IBM Qiskit Live Quantum Seminar Series. In just a minute, I'll be thrilled to roll out today's seminar, number 119, with Shilin Huang from Duke University. Before we begin, number 119, as always, let's give everyone just about a minute to tune into the live stream. Meanwhile, folks, you can get those fingers fired up. As Paul here, our AV, magician, is telling us, you can subscribe so you know when the next Qiskit seminar is coming, and also try to see how to use the chat. We always like to keep it interactive and have a lot of discussions, questions with the speaker, myself, and among you folks in the audience as we go throughout the talk. As you post questions in the chat, I'll bring those questions up to Shilin, and hopefully we can keep this lively and interactive. Now, I see some of you already know the routine here, which is let us know where you're tuning in from today. You can reply to that in the comment chat box on YouTube, located somewhere on your screen, above, below, left, or right. That's the same place where you can post those questions and we can have a discussion as we go through this talk. So thank you for making all the different time zones as always. And let's just dive right into it. Today, I am thrilled to roll out the latest episode of the IBM Qiskit Live Quantum Seminar Series dedicated to you, the research and academic quantum communities. I have the pleasure and privilege of hosting Shilin Huang from Duke University. Hello, Shilin. How are you?
Good. How are you?
Great. Before we dive in, allow me to introduce you to everyone. Shilin is an incoming postdoctoral researcher at Yale University. Shilin recently finished his graduate study at Duke University, advised by Professor Kenneth Brown, who was on the seminar very recently talking about quantum error correction. So go back to that episode if you want to get a bit of a preview there. Shilin is also a research intern at IBM was a research intern at IBM in the summer of 2022, and will tell us about his research focused on fault-tolerant quantum computing and quantum control. So with that, Shilin, I think the stage is yours.
Thank you. Yeah. Thanks, Zlatko, for the very nice introduction, and thanks all the organizers for having me here. And so today I would like to talk about one of my works on fault-tolerant quantum computing, which is with this title, Homomorphic Logical Measurement. And this is a work that has been done in the last summer when I was at IBM, and this is a joint work with my nice two mentors, Thomas Joachim Mokoner and Ted Yoder, who are both researchers at IBM. So yeah, let me see if it works. Okay, so I think many of the audience has been told that we can use quantum computers to do a lot of interesting things. For example, we can run these Shor algorithms to factor very large numbers and maybe crack RSA at some point. And but we need to look at what's the resource we need to perform these large number factoring. So it's very amazing. In 2001, like people can use an NMR quantum computer with 5 or 7 qubits, probably 7 qubits, to factor numbers like 15. Well, it's not impressive in terms of in terms of a classical computing sense, but it's already pretty cool. And nowadays, we're having more and more qubits now. Like now, for example, for IBM Quantum, we have so we have like more than 100 qubits, and these qubits are very, very good fidelity, like approaching 10 to the minus 2, some of them even approaching 10 to the minus 3, and which is pretty nice. But if we want to factor very large numbers, like say more than 2,000 bits, we actually we use way more qubits than this. And like some estimates shows that we need to use like 10 to the 4, 10,000 qubits, and each of them will have every 10 to the minus 14. That's a very challenging thing to do. It's very lucky that we have these techniques called quantum error correction. The rough idea is that you can exchange you can use like multiple physical qubits to encode one logic qubit, so that you don't need to achieve these very low error rate. Say we can use like 10 to the minus 3 error rate to qubits with 10 to the minus 3 error rates to encode less number of logic qubits, but then it turns out the logic qubit will have very low very low error rate, as low as we want. But the price we have to pay is that now you need to increase the number of qubits. Like some estimates, which are done from our friends at Google, show that you probably need to use like 20 million noisy qubit to crack it, like to factor these 2,000-bit RSA integers in 8 hours. And this sounds like a nightmare, and I guess we can already see this very complicated from these picture. And so it's very important to think about how to reduce the overhead of quantum error correction. So if you're working on quantum computing experiment, you might naturally want to think like you can just increase the gate fidelity, or like reduce the error rate you have. For example, if you can make your 2-qubit gates as good as like 10 to the minus 3 error rate, or even 10 to the minus 4 error rate, that could greatly reduce the overhead of error correction. On the other hand, if you're people working in between theory and experiment, you might want to think how to make use of the actual noise in like a realistic noise of the system to make some hardware efficient quantum error correction. One example is this recently developed XZX service code, or many other tricks to perform bias tailored quantum error correction. And but if you're a theorist, you might want to think like maybe we can just come up with like better quantum error correcting codes to reduce the overhead in some sense in a more fundamental way. And what's encouraging is that very recently researchers have developed this like so-called good quantum low density parity check codes, which we won't talk about today, but the topic today will be pretty close to these LDPC business. And so before we talk about LDPC codes, we should look at the current quantum codes we like, the most popular quantum codes we have, which is the service code. It's very nice. It's a code with many nice properties. So one is that it has this so-called two-dimensional nearest neighbor connectivity. That means that your qubits don't need to talk to the other qubits that are far apart. It only needs to talk to its neighbors with these 2-qubit gates. And it also has this so-called very high threshold. That means you don't, as long as your error rate of each gate operation is below some number, say 1%, then you can, and if you have enough qubits, at the end of the day, you'll be able to perform arbitrarily large or arbitrarily long quantum computation. And typically, if your gate error rate is like say 0.1%, that's pretty good. That's already pretty good. And it also has these so-called efficient decoding algorithms. So typically, when you decode errors in quantum error correcting codes, it's a very complicated task in terms of computation, classical computing. But luckily for service code, you have all these like decoding algorithms that can be run efficiently, such as these minimum weight perfect matching or these union find decoders. But I think one more important thing is like it has a very detailed and sophisticated logical operation protocols. And you might heard about these terms like lattice surgery or code definition or twist. Yeah, all of these are developed for service code. So we have very clear understanding of how to run logical operations on these service codes. But there's a very important limitation of the service code, which is actually limited by these 2D locality. So by which I mean, if you consider any quantum codes lay on these 2 dimensions, and here this NKD means like n means the number of physical qubits you use to to encode this code, and K is the number of logical qubits, and D is so-called code distance. And that means when your distance D, the logical error is scaling as this is something like P to the D plus 1 over 2. So if you can increase your code distance, then you can make your error rate arbitrarily low in principle. But for any quantum code on the 2 dimensions, there is this so-called Bravais parameter bound, which says that n, like KD squared is equal to ON. That means if you just want to encode one logical qubit, say then K is equal to 1, then your distance D is at most square root of n. And on the other hand, if you want to have a good encoding rate, that means like you want to have as many logical qubits as possible, then there's a problem that if your encoding rate is not 0, and then your distance is just like constant. So you cannot, when you increase the size of your code, you cannot suppress your error as much as you want. So there's one way to circumvent this difficulty, which is called this quantum LDPC code. The price you have to pay there is that the interaction you have on these LDPC codes is no longer local. So as you can see from this picture, then you can have these so-called stabilizer check that's like far apart in whose qubits are far apart on this lattice, as compared to the previous Toric example, where all these stabilizer checks are just they just form a small, they just occupy a very small region on the lattice. And this LDPC code has this LDPC code stands for low density parity check, and which means that for each stabilizer check, its weight is the weight of this stabilizer check is constant, and also each qubit is only covered by a constant number of checks. And as I said, there's any restriction on spatial locality of these checks. And when you will make your encoding rate K over N to be finite, you can actually achieve some very non-trivial code distance. For example, you can achieve log N distance. You can do like square root of N distance as well. And very recently, people discovered that you can actually achieve linear distance, which is pretty good. So at the end of the day, your K can be ON and your D can be also ON, which cannot be done on surface codes. But of course, there are a lot of challenges to implement these quantum LDPC codes in practice. So I would like to divide them into near-term concerns and more fundamental concerns. So like from an experimental perspective, of course, you want to worry about these long-range interactions when you implement them, because people usually like the qubit interaction to be nearest neighbor or local. But I expect that in the long term, this would not be a fundamental limit, as at the end of the day, we want to implement modular quantum architecture anyways. And from a numerical perspective, the threshold of these the estimated threshold of these quantum LDPC codes are not as high as the surface code. So there are only a very few work on this, and the recent estimations were like 0.2%. And I expect these numbers will get higher and higher over time, because they're only just 1 and 2 numerical work on this. So at the end of the day, we might expect that we don't need a very low error rate to implement these LDPC codes. But from a more fundamental perspective, there are only very few working on to think about how to implement logical operations, how to implement gates or measurements on these LDPC codes. And one way to think about why this is not easy is that it's hard to think about how do you perform individual addressing on these LDPC codes. So if you're working on experiments, you look at these. The qubit that you're looking at are those physical qubits. For example, ions or superconducting qubits or neutral atoms recently. And the idea of individual addressing is kind of clear. You just shine lasers or microwave on your atoms or artificial atoms. Then and you just want to make sure that you're controlled when you adjust one particular qubit. You don't accidentally make crosstalk on the other qubits. Then you'll be good. And if you're working on surface code, then these logical qubits, they're also separable in the sense that like these two logical qubits, like any two logical qubits won't overlap together. So you also have this clear sense of how to individually address each logical qubit on these surface code lattice. But for these quantum LDPC codes, all of these logical qubits, they will be compact. They'll be encoded in a very dense and compact way, so that all of these like logical operators, they will actually overlap to each other. So it's hard to think about how to extract a particular logical qubit of information on these very compact blocks. And currently, there are like around like 5 or 6 works on, maybe more than that, like but it's no more than 10 definitely, to think about how to encode, how to perform logical operations on these LDPC codes. The earliest pioneering work is done by Daniel Gottesman, where he uses this state distillation or gate tabulation ideas to perform logical gates and measurements. But it turns out it has a very non substantial overhead there, and there are also some other works on logical gates on some specific codes. But I would like to highlight one of these work, which is done by Cohen, Kim, Bartlett, and Brown. They actually generalize these ideas code definition from surface code to perform arbitrary logical Pauli measurements on these arbitrary quantum LDPC codes. And the idea is that you can use another code patch to glue on your original quantum LDPC code block, and then you can use that to perform Pauli measurements, logical Pauli measurements, such as XX or ZZ or even XZ measurements, and which is very nice. The only downside there is that it's the space-time overhead is still not quite well known, or maybe I should say put in this way, like when you perform logical measurements, it requires say D rounds of error correction there, then which sort of slows down your logical operations. So yeah, I think I should go back to the motivation of my work. So this idea of code definitions comes from the surface code, and it's about logical operations with local interactions. So like you're not allowed to perform any arbitrary 2-qubit gates on your qubit lattice. Then how do you perform gates on that? And that's all about code definition. But this quantum LDPC code is non-local anyways, so it's not necessary to stick on these code definition ideas. So if we look at if we look at the history and to look at how do people perform logical operations on very small block codes, it's actually even more. It's actually more straightforward. You can use some Ancilla block to interact with your data block with these 2-qubit gate network, and then measure the answer to perform these logical measurements. And I would talk about later, like one of these these ideas known as Shor, Steane, or Kineo methods. And but it's kind of unfortunate that these ideas are not directly applicable on large LDPC large quantum LDPC code blocks. So our work was to think about how do we generate this idea to equip.
Yeah, sorry, I was going to let you finish, but and I think you'll probably talk about this, but maybe if you just give us the broad motivation for why they're not directly applicable in LDPC codes.
I will talk about it later. Yeah.
Okay, perfect. Thank you.
Yeah. So yeah, we will discuss like why these ideas are not directly applicable, and then how to circumvent these difficulties by some new construction.
Okay, great, awesome, thank you.
Okay, so yeah. So before we go into details, let's just make sure everybody's on the same page. So I guess many people had heard about these CSS or Caldebank Shor and Steane stepwise codes. The rough idea is that you use on these many physical qubits, you define a group of commuting Pauli operators, and use them as your stabilizers of your quantum code. That means you consider the +1 common eigen subspace of these Pauli operators within this group, and then you, if there are no any error, when you measure these stabilizer, you will always get the +1 outcome. But if you get any -1 outcome on some particular stabilizer checks, then you will you know that there are some errors in your system. And in particular, if you're in this talk, if we are mostly focused on this CSS code, that means you can divide your stabilizer into two subclasses, like subgroups, and each, like for example, this XX only consists of X-type polys, and SC only consists of only Z-type polys. And one famous example is this 713 Steane code, as I shown here. And as I said, we need to perform measurements to know what errors happens in the system, or if we want to perform, we want to perform logical measurements. So that's done by measuring these many-body Pauli operators. So for example, here, if we want to measure these Pauli operators P1, P2, P3, and P4, and then we just prepare using, we can, a very naive idea is that we can use Ancilla qubit, preparing the plus state, and then perform these control Pauli gates, like control P1, control P2, control P3, and control P4. And after that, we measure these Ancilla qubit in the X spaces. So if it turns out that you get a +1 outcome, then you know that you're performing your logical P measurement. Your Pauli P measurement will be +1. Otherwise, you'll get a -1. And but there are a lot of troubles of these idea. One problem is that in these circuit network, if you have any errors in between these CNOTs, they can propagate to your data block. So for example, here, if you have an X error, Pauli X error between the second and the third 2-qubit gate, they will propagate to the data qubit and become two errors P3 and P4. And then turns out these when you measure these logical operator, which has weight at least D, the weight of these correlated errors can be any number from 0 to D, which is very damaging. So, and on the other hand, if you just have a very simple measurement error on your measurement, they will lead to incorrect logical outcome. So that means that your logical measurement is not reliable at all. So, so the first idea of overcoming these two issues done by, I think it's done by Peter Shor, and it's known as Shor measurement. The rough idea is that you can, instead of using one single Ancilla qubit, you can prepare a large block of JZ state or cat state, like all 0 plus O1, the superposition of all 0 and O1. And then you can run these so-called transversal 2-qubit gates from Ancilla to data, where the Ancilla is the control and the data is the target. And then after that, you can just measure all the qubits of the cascade of the Ancilla state in X spaces and take the parity of them as your logical measurement outcome. And one way to think about it is that these cascade or GSD state is actually these logical prostate of these quantum replicating code. So we're just replacing the original single plus state of these single qubit into a logical qubit, and that prevents a lot of that prevents this problem of error propagation, like errors on, as long as you can prepare your cascade fault-tolerantly, any error on these cascade will not propagate to multiple errors on your data block. But still, this idea is not robust against measurement errors. If you have any parity flip, measurement outcome flip on these qubits, Ancilla qubit or Ancilla measurement, it will flip the logical measurement outcome. And so to deal with that, we need to repeat our measurement. So here, for example, for this 7-qubit Shor Steane code, we can repeat measuring the logical operator for 3 times. And if any of these measurement is flipped by error, we can simply take the majority vote to get the logical measurement outcome. But there's one very annoying error, which is, for example, if you have an X error on your data block, and they can actually propagate to all of these measurement circuit. So like a single error can already flip all of these measurement outcomes. So taking the majority vote seems not helping us. But luckily, we can actually perform fault-tolerant error correction in between these logical measurements, so that these X error at the beginning of the circuit would not propagate to further to the later logical measurements. So when you take the majority vote, you will still be fine. And this error correction is done by repeatedly measure the stabilizer of the code, and which we can leave as a black box in this talk. And the reason why, as I said before, like I made a claim that Shor measurement would not work well for large code blocks, and the reason is that if you calculate your the logical measurement error rate per measurement round carefully, it actually, like if we assume each physical measurement is flipped by a probability p, and then it turns out the total error rate of this logical measurement is exponentially close to 1/2 as your code distance d increases. And to distinguish between so it's very close to random outcome. So if we want to distinguish between +1 and -1, it actually requires an exponential number of repetitions there. But we need to keep in mind that in our quantum computation, we're not supposed to perform exponential number of operations in our code. So that if that's the case, then we won't have any advantage in terms of computation. And so one other idea to deal with this issue is called Steane measurement, which is invented by Andrew Steane in 1990s. So the observation here is that for the CSS code, we actually have a very natural way to perform logical control NOT gates in between logical qubits, which is simply just applying these transversal CNOT network. Like these CNOT gates are performed on these 2 corresponding qubits on each 2 different blocks, so that after you perform all these transversal CNOT, you automatically perform a transversal CNOT on these k logical qubits. And we can actually use an identical code block as your Ancilla to perform this logical measurement. To see that, let's look at a special example where you only have one logical qubit, and at the logical level, we just prepare your logical qubit in the plus state, and then perform these CNOT gates, and then measure your Ancilla qubit in the X basis. And then we can simply translate these logical circuit into a physical circuit, and then everything is good. And after you measure all the qubits in X spaces, you just simply take the corresponding parity to know your logical measurement outcome. And similarly, if you want to perform logical Z measurements, you prepare your Ancilla in 0 state and perform your logical CNOT in the reverse direction, and then measure all the qubits in the Z basis. And if we look at so we need to think about how do we fault-tolerantly measure the logical operator. So let's take this Steane code as an example. So the nice thing here is that when we measure all the qubits in the Z basis, we're not only just extracting the logical outcome as in the Shor cases, we also have these measurement outcome of these 3 extra parity checks. So if you have any measurement error on these qubits, it not only flips the logical outcome, but it also flips these 2 parity checks. So you can use that. You can use that as an information to correct errors on your on these classical outcomes. So after you make the error correction, your logical outcome will be extracted in a more reliable way. And similarly, if you have the errors on the data qubit, although you will propagate down to the Ancilla qubit as well, but it only flips one particular Ancilla readout, so it wouldn't affect your logical measurement outcome that much once you perform error correction. So basically, these Steane measurement is robust against measurement errors and errors on data qubits, and particularly can tolerate. It can basically tolerate d-1/2 errors in total, which is obtained by the fact that all these error correction codes of distance d can correct d-1/2 errors, and because of this, your logical measurement is robust, and there's no any need for repetitive measurements. But once you have multiple logical qubits, the circuit is slightly more complicated. Your Ancilla qubits, your Ancilla block needs to be prepared in some other more complicated state. For example, here, if we want to perform logical ZI measurement, the Ancilla state you have will be like all these other logical qubits are still preparing the plus state, so that when you perform these transversal CNOT, they won't do anything on these other logical qubits, but your logical qubit I is still prepared in the 0 state. So these transversal CNOT will, in the end, will entangle your Ancilla qubit I and your data qubit I as well. And then after you measure all the qubits in Z basis, you can fault-tolerantly read out the logical ZI measurement outcome. And you can also use this to perform logical ZI ZJ or Bell measurements, or 2-qubit Bell measurements. The only thing you need to do is that you, instead of preparing 0 and or plus, we prepare logical Bell state in qubit I, between qubit I and qubit J, and all the other remaining logical qubits are still prepared in the plus state. If you are familiar with stabilizer formalism, you can think of this state as a logical state that's stabilized by logical ZI ZJ, which is the logical operator you want to measure, and all the other logical stabilizers are X type, which commutes with these logical ZI ZJ. So they are basically Xi, Xj, and or like XL, XL, where L is non-I and J. Yeah, and yeah, but it looks pretty nice. But when you think about how to, I didn't address this problem of how do we prepare these Ancilla state. So when you really think about it, one naive idea is that you can, for example, you can first perform a non-fault-tolerant entering arbitrary unitary circuit, well, not arbitrary, but like an unitary encoding circuit to encode your k logical qubit of information into these n qubits. And then since we know that the circuit is not fault-tolerant in a way that errors can propagate to many places, and we need to run some verification process. For example, here we can measure some particular stabilizers or check operators, or or logic operators, to see if they are in the correct value. If not, some of them becomes -1, or if any error triggers these measurement or verification, we just discard the whole block and repeat the whole process until it passes this verification. But turns out once your code block becomes larger and larger, the verification or post-selection success rate will decay exponentially as your code block size increases. And so basically, for large code, it's very hard to hope for the success of a code block, of a code block preparation. And there are some other techniques called state dissolution or concatenation to deal with this issue, but they all have very large space overhead. You can see here, like, to distill one particular logical state, you probably need like 9 or even more, way more. You need to prepare a lot of copies of your Ancilla code block and then distill them. And at the end of the day, only one will survive. Yeah. So this is not what we want. So there's one interesting case. If we go back to the case that where we only encode one logical qubit, there's one simple way to prepare these logical state without any post-selection, which is you can actually prepare all Ancilla qubits in the 0 state, and then project the state into the code space by measuring all these X-type stabilizer generators. Here, basically, since all the physical qubits are preparing the 0 state, you automatically have those Z-type stabilizers generators. They're already fixed, so you don't need to measure them. But after you project the state into the code space, you need to run some fault-tolerant error correction procedure to correct these measurement errors or existing errors on a data block. But after the error correction, you will already have a logical 0 block, and there's no need to post-select these logical state. The downside of this trick, well, this trick can be generalized to some k-qubit logical state, but it can only be used to prepare some particular states, such as 0k state or the 1k state, or maybe a mixture between 0 and 1. But you cannot prepare any states such like which is a mixture between 0 and plus. So you cannot prepare plus 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 0 plus plus plus, or you cannot prepare the Bell state as well, because the deep reason there is that these state consists of both X and logical X and Z-type stabilizers. So you can only make sure that one type of logical operator is robust against errors. And so, as a summary, we can compare these Shor and Steane approach. So the nice thing here is the very special case here is like, okay, if you only have one logical qubit, then you can just run Steane measurement, because there's no need for any post-selection. Also, it's a very deterministic protocol. And but if you have multiple logical qubits, then You might just want to do Shor measurement, but it requires an exponential overhead as well. That's not what we want to have. And or we just pay the cost of very expensive state preparation, but with just one round of logical measurement using the Steane method. But a natural question can be asked here, which is, can we actually think about other? So here we only look at two types of codes. One is the quantum repetition code, which is the Shor measurement case. The other one is the same code as your data code, which is Steane case. But are there any other choice of Ancilla code such that you don't need to pay this pain of you don't need to face this pain of complicated state preparation, or you also don't need to repeat your logical measurement. So that's the most important question for this work. So and in particular, to do that, these Ancilla code need to satisfy few conditions. Two conditions. One, it only encodes one logical qubit, so that similar to the k=1 Steane case, you don't need to repeat your state preparation for an exponential amount of time, and it also has distance d, and that will give you these single shot or one shot logical measurement. So there's no need to repeat your logical measurement. Yeah. So here comes this idea of so-called homomorphic measurement. Yeah, I won't talk about why we picked that name until the end. So if we really have these another code of parameters M1D, when you measure so then you only have one Ancilla logical qubit. So when you measure logical Zi, we want to the interaction between your data and Ancilla should be some unitary that implements the logical CNOT gate between your data qubit I and your Ancilla qubit. And if you want to measure, say, logical ZI/ZJ, the unitary U should be a composition of two CNOT gates. One is the CNOT between data qubit I and the Ancilla, and the other one is the CNOT between the data qubit J and the Ancilla. And after that, you measure your M1D Ancilla code in Z basis and run some error corrections on your measurement outcomes, classical error correction, and then you will obtain your logical measurement outcome in a reliable way. But the obvious downside here is that the construction of the Ancilla, I haven't talked about how to construct this code, and it's sort of obvious that the construction of Ancilla code will depend on the structure of the data code and what kind of logical operators you want to measure here. So it's at this stage, it's hard to think about how to have a very general construction for all the cases. So we just look at in this work, we just look at a very specific example of which is basically the Toric code and its generalization. One interesting, I will talk about later, one interesting example is the hyperbolic surface code, which is one kind of quantum LDPC code with finite rate. But here, let's look at this example of Toric code. So, these on these Toric code lattices, we put edges on these qubits. Sorry, we put qubits on these edges, and then for each vertex or each star, and we have these X-type stabilizer checks, like XXX on these red star, and on these on each face or each pocket, we have these Z-type stabilizer generator, ZZZZ, like which are shown in this blue region. Sorry, blue square. And this code encodes two logical qubits. And so if you think about what is the logical Z1, it is actually you can think of it as a string on these a loop on this lattice that's not contractible on the torus. So for example, logical Z1 is a horizontal loop, goes around the torus, which are shown in this green line. And logical Z2 is in another direction, which is a vertical strip, vertical loop in this yellow line. And logical X type operator are making cuts, basically making cuts on the torus. For example, this logical X1 is a vertical cut of the torus, while this logical X2 is the horizontal cut of the torus. And you can check like the support of say logical X1 and logical Z1, they only overlap with on exactly one qubit, so they anti-commute. But logical Z1 and Z2 or logical Z1 and X2, they'll commute again. They will commute, so the commutation relations on these logical operators are preserved. So now let's think about how to measure logical operators. If you visualize, we can visualize these Shor measurement or Shor style Ancilla as a loop, like as a loop. That's like that represents these quantum repetition code as well. And then we just put a loop on the top of the torus and then perform these transversal control NOT gates between these data sheet and the Ancilla ring. And then that's basically the circuit of the Shor measurement. And you can think like this, you can think of it this way, like these Shor Ancilla is too thin to be robust against measurement error. And so on the other hand, Steane Ancilla or Steane measurement, in Steane measurement, the Ancilla is basically the whole torus, which are shown in this blue region. And then we perform these transversal CNOT gate between two torus. And the problem here is that you want to prepare your Ancilla code block in these I need a state at 0+, which is not or 0 or or plus. That's a complicated task to do. And so, yeah, one interesting construction is that to have is we can actually cut this the Ancilla torus and make it as like a ribbon. And this is done by removing some of these qubits in these in this gray region, and then you can check that these this will be a surface code that only encodes one logical qubit, because there's only one non-contractable loops on these on these ribbon, and basically the logical like the logical X operator of these Ancilla ribbon is that you just cut the ribbon you can just cut the ribbon, and then that's basically how you perform this logical X operation. But because this ribbon is wide enough, so it has this width d, maybe d-1, but if you think about it in terms of code distance, it's a code of distance d, but it only encodes one logical qubit, and you can still perform transversal control NOT gates between these blue this ribbon that's shown in blue and the original data torus, and you can use that to perform logical Z1 measurement without any need of post-selected Ancilla state and repetitive measurement. So the general idea is, okay, now we can think about the general idea of how to perform arbitrary logical measurements, or X-type or Z-type logical measurements, which is basically just think about like try to construct some ribbon that winds around the torus and follow the logical operator path on the torus, and yeah, and these ribbon has to be wide enough so that it has it's it actually, and so then it encodes an M1D code. But so, and the problem is, how do we construct these ribbons in general? So it's in particular, if we look at the logical Z1, Z2 operator of the torus, you can think of it as like two loops putting together. And a nice idea to construct these ribbon is to think about the neighbor, to find neighbor on of these logical operator path. But we want to make sure that it only encodes one logical qubit. And here, if we think about the neighbor of these green circles, like which are two circles, and no matter how you choose your neighborhood, these neighborhood always encodes two logical qubits, and that's not what we want to have. And so to circumvent this problem, we can actually, instead of just using one layer of Ancilla qubits, you can actually introduce two layers of Ancilla qubit, so that, like, for example, yeah, I guess probably the audience cannot see the cursor, but you can think about these loop in this way that, like, when you go back to these intersection points, so when you go to this intersection point, you can turn the other way, and then once you go back to the point, it doesn't really go back to the point on these two layers. So for example, on the left, so typically on the torus, when you go around the torus by one circle, you will go back to the original point. But here it's lifted to the other layer, and then you go around the torus on the other way. But then after that, you will go back to the original point. So, and these the Ancilla code construct in this way is just we only have one logical operator loop, so that it only encodes one logical qubit, and you can still have like a wide enough width to have good codistance. Yeah, and so like this is a very intuitive way to think about it, but to describe it in a mathematical way, we have to introduce some language to describe it formally. So to actually find these Ancilla codes, what we're actually doing is that we first basically make this torus. We first view this torus as introducing periodic boundary conditions on the lattice. Like we can imagine like an infinite square lattice, and then we say that, okay, if we go east for D units, we say that we enforce them. We go back to the same point. If we go to the north for another D units, you also go back to the same point. And that by enforcing this periodic boundary condition, we obtain this torus. But to construct these Ancilla blocks, we can first remove all these periodic boundary conditions, so that this logical operator will no longer become a loop on the lattice, but becomes like a path that connects two different points. And here, when you, for example, for this logical Z1 Z2 operator, is their path connects a point x, y, and some other points x plus d, y plus d, and then we can find the neighborhood of these paths, and then finally comes back to the original torus lattice. Then these at the Ancilla code we construct in this way doesn't only encodes one logical qubit. It doesn't encode two or multiple. Yeah, this is very detailed. There's a very detailed math description using these so-called theory of covering space there, but I won't want to go into very deep details. But this trick can work for arbitrary surface code on arbitrary, so like surface code on arbitrary closed manifold. And one useful application of our trick is that we can look at another type of surface code called hyperbolic surface code. These surface code are defined on these hyperbolic manifold. The upshot there is that it can encode. You can use that to encode like linear number of logical qubits. So your encoding rate is finite. But then instead of only just getting constant distance, you can have like log n distance, log n distance. And yeah, I shouldn't say this is best known, but like currently they have very good parameters. So if you compare like if you fix k and d using and for example here, if you have like 488 logical qubits and distance 12, if you use the hyperbolic surface code, you only need to use like less than 5,000 physical qubit to finish this encoding, to perform this encoding. But if you use the usual planar surface code, it would take kd square physical qubit, which becomes like 70,000. And similarly for other coparameters, like k equals to 960 and d equals to 10, this hyperbolic surface code is like a significantly outperforms the planar surface code in terms of number of physical qubits. And all these ideas we develop for the Toric code can be immediately applied for the hyperbolic surface code. The only difference is that these symmetric group or the periodic boundary condition on the hyperbolic surface code is more exotic. But I'm not going to talk about details here. But all these procedures are basically the same thing. So that you can basically, no matter how complicated your hyperbolic surface code is, like no matter how these logical operator overlaps together, we're still able to perform arbitrary Z-type logical or X-type logical measurements on these hyperbolic surface codes. Yeah, I think that's almost the end of my presentation. So as a summary, we just look at we basically look at these traditional ways to perform logical measurements on small codes, and then we figure out some of the problems when these ideas are applied to larger LDPC codes. But we propose these so-called homomorphic measurement, which uses a different choice of answer qubits, and by carefully choosing the appropriate answer code, we are able to circumvent the need of post-selection of answer states, and there's any need to perform repetitive measurements. So that greatly, in principle, greatly reduce the overhead of logical measurements of these previous methods using transversal control NOT gates. So here we only think about how to perform these logical measurements on surface codes or its variants like hyperbolic surface code. But it's very natural to think about how to generalize this idea to other type of quantum LDPC codes, such as these hypergraph protocols or this recently discovered elliptic protocols or balance protocols of very good distance and rates. But like our method of our construction uses very uses a lot of like geometric intuition, but like all these other codes are constructed in a very algebraic way, and in particular they use these idea called chain complex that arise from these math these are homological algebra. And can we actually think of it in these are more algebraic way to construct logical measurement protocols for other codes. That's a very interesting open question. But what things think and I think that's the point I can explain why this is called homomorphic answer. So in very mathematical, if we describe it in a mathematical way, your CSS code can be described by these chain complex like C2, C1, C0. It doesn't matter what it means, but that's just one way to think about CSS codes. And your Ancilla CSS code can be described by another chain complex. And there's a map, and all these possible logical measurement protocols using transversal CNOT gates can be thought of as like a mapping from these the Ancilla chain complex to the data chain complex. And in mathematics, that's called like a chain homomorphism. And that's basically how we come up with this name homomorphic Ancilla. But we still don't know how to construct the Ancilla chain complex or Ancilla code for a more general LDPC codes. Yeah, that's if anyone is interested in going to this direction, then I'm happy to talk to. And yeah, and that's the end of my talk. So I'd like to thank my co-authors, Thomas and Ted, for collaboration. And I think I would also like to thank my advisor, Ken Brown, and and also Andrew Kloss, who is my manager when I was at IBM for intern. So they all encouraged me to think about this direction, and which at the end come out, we have these results. So yeah, I also want to thank in general the IBM summer internship and IRP's Logic Cube program. With that, I will take any questions. Thank you.
Thank you, Shilin. That was very nice. And I know at least I saw Thomas here in the chat earlier. So if you're still with us, hello. And it's also great to see this work from your internship and to see how useful and valuable the whole internship experience, I guess, has been in your experience. And yeah, there's very nice results. I think you addressed actually a lot of the questions in terms of what's the outlook and how do you combine this, or think about this with LDPC codes. There were some questions around that. Maybe if you just summarize for us again, sort of the main obstacle that the community has to overcome, from all the lessons you've seen here and seeing, like, if we had to try to distill that down into, what is the recurrent theme that we need to get over? Yeah, how would you try to summarize that?
Oh, that's a good question. So I think maybe I should put it this way. So like, general, when you design a logical gate protocol or and a code, you need to think about many things. Like, what is the space overhead of this protocol, and what is the time overhead as well? Like, how many, like maybe some protocol like these transversal gates, they can be performed in just constant time. That's pretty good. But like in general, we might want to repeat the measurement for multiple rounds. So, and what is the actual time overhead there? And also, how do we decode errors in these fault-tolerant measurement or fault-tolerant operation protocols? That these are basically three most important questions in my opinion. And currently all these quantum, for these all these quantum LDPC code logic operations, they're either not general enough or they're general enough, but the space or time overhead is not guaranteed, or maybe there's no good decoder for it. So, and maybe one example is this nice Cohen paper. So there, usually the problem I can see from that paper is that when you for most of these LDPC code, they support these so-called single-shot error correction. That means your error correction only need to be performed for you only need to perform one round of error correction measurement, or syndrome measurement to correct errors. You don't need to, unlike surface code, you don't need to repeat D rounds. But turns out, like, when you perform logical measurements using the Cohen paper as results, it's very likely that you have to perform D rounds of error correction there as well, which is very different from the quantum memory case. So, and very interesting question to ask is, like, is this always necessary to have D rounds of time overhead, or maybe there's some way to perform very fast readout logical measurement or logical gates on arbitrary LDPC codes? If that's possible, then that would be awesome. Yeah, but that's basically what I learned from these projects. But
okay.
Yeah.
Thank you. And a very common topic on this seminar has been error mitigation rather than error correction. I wonder if you have some perspective on us, if error mitigation will be useful at the time that we do have quantum error correcting codes, or maybe at the beginning, or how, if you can maybe add some perspective on how those two may interplay in the future, sort of not in the next 1-2 years, although maybe that is where we should think as well, but even further out. So feel free to give us, I know this is maybe a slightly broader topic, but it'd be interesting to see. I know this is a question that has come up a lot throughout.
Let's see. To be honest, I'm not an expert in error mitigation at all. But what I can expect that, like, maybe I think there might be already some work, but like we might be able to think about how do we perform error mitigation at the logical level, so which should be compatible with this error correction as well. But I don't know enough to say too much about that. Yeah.
And that is, you mean because error correction doesn't like fundamentally solve your problem, just suppresses your errors arbitrarily small?
Sorry, can you repeat that again?
Well, maybe that's a much longer discussion. That's we can table that one. But it's an interesting question because the whole, almost every other experimental talk we see now has been related to error mitigation work. And maybe a final question. There's a question from Ron. Let me see if I can understand. With respect to one of the slides where you showed earlier, and hopefully we can remember which slide that is. So hopefully, Ron, you can clarify. Does drawing a Z-gate inside of the AND symbol have a specific meaning?
Drawing a Z-gate inside of an AND symbol.
So let's see if we can figure out which slide this was. I think this was quite earlier on. By the way, nice graphics.
Thank you.
Maybe, yeah, I'm not sure. Ron, feel free to clarify. I think we're not quite clear which slide you're referring to. And by the way, while on your graphics, what do you use to make those 3D plots? Just out of curiosity.
Oh, I think I just use Illustrator. Illustrator is not really a 3D one. I didn't use like SketchUp or others to generate these figures. Yeah.
Okay, excellent. Well, Shilin, I see we're 10 minutes over. So folks, thank you very much for tuning into Shilin's talk and for all the questions throughout the presentation. Shilin, if you'd like to leave us with any final words, this is a good time to do that.
I guess just not in particular, sorry.
Excellent. Well, with that, Shilin, thank you very much for accepting our invitation to talk at the IBM Qiskit Live Quantum Seminar Series. Folks, this talk will stay up and recorded, so you can go back and rewatch it, but you can only have these discussions live every Friday at noon Eastern Time. And with that, we will see you next Friday at noon Eastern. Have a great day.